Welcome everyone. I am Dr. Rajesh Singh and in this video I have solved questions that I gave to my students as an open book test. You all can also take this test if you want to do so and can come back to check its solution. I have shared link of the test in the description of this video. You can download the test from there. Also, if you have any doubts, then you can write me in the comment section and I will be happy to help you out. So let's start with question number 1. So in question number 1, we have to show that 2 is the only limit point of the set A. The set A consists of the point of the form 2 plus 1 by n where n belongs to n. So question 1, given A is equal to 2 plus 1 by n, n belonging to n. To show 2 is the only limit point of A. So this question is similar to the question where we show 0 is the only limit point of this set 1 by n, n belonging to n. So instead of 0 here we have 2. So first we will show that 2 is the limit point of A and then we will show that any point other than 2 is not a limit point of A. So let C belonging to R be any real number. So case 1, C is equal to 2. So in this case we will show that C is a limit point of A. So let epsilon greater than 0 be any real numbers. Then by Archimedean property there exists M belonging to Z positive such that 0 is less than 1 by M less than epsilon. So what Archimedean property says? It says that between any two, if I take any positive real number, then I will always be able to find a number of the form 1 by n, 1 by m between 0 and epsilon. So by Archimedean property, we have an m belonging to z positive such that 0 is less than 1 by m is less than epsilon. Now then 2 plus 1 by m belongs to the interval 2 minus epsilon to 2 plus epsilon. So this implies So this implies 2 minus epsilon, 2 plus epsilon intersects A at a point other than 2. Hence, now since epsilon greater than 0 is arbitrary real number, so by definition of limit point, 2 is a C equal to 2 is a limit point of A. Now we will show that if I take any other point, then C is not a limit point of A. So let C be less than equal, strictly less than 2. Then in that case, minus infinity to 2 is a neighborhood of 2 and minus infinity to intersection A is empty. So we have found a neighborhood of C which does not intersect A. So this implies C is not a limit point of A. Let us go to case 3. Case 3, C is greater than 3. Then again Then again 3 to infinity is a neighborhood of C which does not intersect A. Hence, by definition, C is not a limit point of A. So we have shown that if C is less than 2, then C is not a limit point. If C is greater than 3, then C is not a limit point. Now, case 4, C is equal to 3. So in this case, the nib so in this case, 2.5 to 3.5 is a neighborhood of C which does not intersect A. Hence, C is not a limit point of A. Now next case 5, C belongs to 2, 3 and C does not belongs to A. In this case, there exists M belonging to Z positive such that C lies between 2 plus 1 by M and 2 plus 1 by M plus 1. So now 2 plus 1 by M plus 1 to 2 plus 1 by M is a neighborhood of C which does not contain, which does not intersect A. Hence, C is not a limit point of A. So we are just left with the final case, which is the case when C belongs to A and C is not equal to 3. So in this case, C is equal to 2 plus 1 by M for some M belonging to Z positive, then 2 plus 1 by M plus 1 and 2 plus 1 by M minus 1 is a neighborhood of C such that 2 plus 1 by M plus 1 and 2 plus 1 by M minus 1 intersection A minus C is empty. So this implies C is not a limit point of A. So in all the cases except C equal to 2, we have shown that in all the cases except case 1, we have shown that C is not a limit point of A. Hence, 2 is the only limit point of A. So this proves question number 1. Now let us see what is question number 2. So question number 2 is we have to show we have been given that fx is equal to sine 1 by x and we have to show existence of a sequence xn in R minus 0 such that xn tends to 0 but fxn does not converge in R. So what we will do in this case, So we have given fx is equal to sine 1 by x for all x belonging to r minus 0 to show there exists sequence xn in R, xn not equal to 0 for all n belonging to n such that xn converges to 0 but fxn does not converge in R. So this is, we have to construct a sequence of this form such that xn converges to 0 but fxn does not converge in R. So for this what we will do, as we, if you remember, we did a question where to show limit x tends to 0 sine 1 by x does not exist. So for this we took two sequences xn. So we took two sequences. We took xn equal to 1 by 2n, 1 by n pi, and yn we took equal to 1 by 2n pi plus pi by 2. And for this we showed that xn converges to 0, yn converges to 0, and fxn is constant sequence 0 and yn was constant sequence 1. So this is what we showed. Now what we will do is we will take the two sequences alternatively, and this is how we will construct our required sequence in this question. So what we will do, we will take let xn equal to n pi if n is odd, 1 by n pi if n is odd, and 1 by n pi plus pi by 2 if n is even. So this is how we are taking xn. So this we deduce from yn and this we reduce from xn. So we are constructing a sequence xn such that xn is equal to 1 by n pi if n is odd, and xn is equal to 1 by n pi plus pi by 2 if n is even. So for this sequence, clearly for this sequence xn converges to 0. Now what is f of xn? Let us see f of xn. F of xn is equal to sine n pi if n is odd and sine n pi plus pi by 2 if n is even. So this is equal to sine n pi is 0 if n is odd, and sine n pi plus pi by 2 is, because n is even, so it is of the form 2m pi. So 2m pi plus pi by 2 is equal to 1. So this is 1 if n is even. So f of xn is an this f of xn is an oscillating sequence. It is 0 1 0 1 and so on, is an oscillating sequence, and is not convergent in R. So we have shown existence of a sequence xn. So this is the sequence xn. This is the sequence xn, 1 by n pi if n is odd, 1 by n pi plus pi by 2 if n is even, such that for this sequence xn converges to 0, but fxn, which is the oscillating sequence 0 1 0 1, is not convergent in R. Now next we were to deduce that We were further asked to deduce that limit x tends to 0 sin 1 by x does not exist in R. So for this we just need to use divergence criteria. So then by divergence criteria for limits, limit x tends to 0 sin 1 by x does not exist in R. So this completes the proof of question number 2. Now let us move to question number 3. So what is question number 3? So question number 3 is we are given that we have to find limit using epsilon delta definition and we have to solve these two. So first let us take the first part, which is limit x tends to 4, 2x plus 3 upon 8x plus 1 equal to 1 by 3. So for this what we will do, okay, we start with question number 3 first part. So we have to show, limit x tends to 3 or 4, 2x plus 3 upon 8x plus 1 equal to 1 by 3. So for this what we will do, we will let epsilon greater than 0 be any real number. So we have to show there exists delta greater than 0 such that 0 less than x minus 4 less than delta should imply 2x plus 3 upon 8x plus 1 minus 1 by 3 less than epsilon. So for this what we will do, we will express this in terms of x minus 4. So consider 2x plus 3 upon 8x plus 1 minus 1 by 3. So this I can express it as 6x plus 9 minus 8x minus 1 upon 3 times 8x plus 1. So this is equal to minus 2x plus 8, 3 times 8x plus 1. So this can be written as 2 by 3 8x plus 1 x minus 4. So now I have to find some k such that this is less than k. So for this I will have to take some bound on x minus 4, but for that I have to, because this x is in denominator, so I have to first equate this to equal to 0. So for this what we will do, this is rough, so you don't need to write. So 8x plus 1 equal to 0 implies x is equal to minus 1 by 8. So when I will write x minus 4, so this becomes minus 33 by 8. So this implies mod x minus 4 is equal to 33 by 8. So x less than this, any x less than this, and this is approximately 4 point something. So I can take any x less than 4 and that will work for me. So let x minus 4 equal to less than x minus 4. So this is the bound we are taking, less than 2. Then this implies minus 2 is less than x minus 4 is less than 2. And this implies 2 is less than x less than 6. So this is our star. So this implies I will multiply both sides by 8. So what I will get this, and if I will add, so I will get 8x plus 1 less than 49. Now since mod 8x plus 1 is greater than equal to 8x plus 1 and this is greater than 17. So using 8x plus 1 greater than 17 in star, we get 2x plus 3, 8x plus 1 minus 1 by 3 is less than. So when I will replace this by star, so this will be 2 upon 51. So 2, 3 into 17 x minus 4. So this is equal to 2 by 51 x minus 4. So my k is this. So what will be my delta? So I can take, let delta equal to, so what delta I can take? I can take delta to be equal to 51 by 2 epsilon. So minimum of 51 by 2 epsilon, and the bound that I took, the bound was 2. So for this delta, for the above choice of delta, it is clear that 0 less than x minus 4 less than delta implies fx implies 2x plus 3, 8x plus 1 minus 1 by 3 is less than epsilon. Hence, limit x tends to 4, 2x plus 3 upon 8x plus 1 is equal to 1 by 3. So this is what we have shown. Now, what is the second part of this question? Second part is, we have to show limit x tends to 3, x plus 4, 2x plus 3, 4x minus 5 is equal to 1 by n. To show limit x tends to 3, x plus 4, 2x plus 3 is equal to 1 by 9. And what was this? 2x plus 3, 4x minus 5. 4x minus 5. So this is what I have to show. So for this, what I will do, I will let epsilon greater than 0 be any real number. So I have to show there exists delta greater than 0 such that 0 less than x minus 3 less than delta implies fx. Fx is not, we have not chosen fx, so we will directly write x plus 4 to x plus 3, 4x minus 5 is minus 1 by 9 is less than epsilon. So for this, what we will do, we will express this in terms of x minus 3. So consider x plus 4, 2x plus 3, 4x minus 5 minus 1 by 9. So this, if I simplify, I will get 9x plus 36 minus 8x square minus, so this will be plus 10x minus 12x plus 15 upon what we get 8x square minus, so plus 2x minus 15. So this is what we get. Okay, so this is equal to, if I will simplify it, so I will get minus 8x square, then I am getting plus 7x and plus 51 upon 9 times 8x square plus 2x minus 15. Since I want to get x minus 3 in this, so I will have to divide the numerator by x minus 3. So what, let us see, we are given x minus 3. So what I will get, this is 8x, so 8x square minus 24x minus plus, so this will become 17x minus 51. So I will multiply this by 17. So I can write that this is my rough. So I can write that as 8x plus 17 upon mod x minus 3. And what was that? 9 8x square minus 2x plus 15. Oh, this was plus and this was minus. Let us look at that. Yes, 8x square plus 2x minus 15. So this is what we have got. Now I can use triangle inequality, but we will use triangle inequality only in the numerator, because if we will use in the denominator, then we may not be able to save out this less than equal to. So this is equal to 8 mod x plus 17, or 17 is positive. So to need the modulus signature, 9 times 8x square plus 2x minus 15. X minus 3. So now what we have here, so we need to put some bound on this, but for that we have to equate the denominator to 0. So 8x square plus 2x minus 15 equal to 0 implies 2x plus 3, 4x minus 4x minus 5 is equal to 0. And what does this imply? So this implies x is equal to minus 3 by 2 or x is equal to 5 by 4. So what is x minus 3 is equal to, so if I take x minus 3, it will be minus 9 by 2, and x minus 3 in this case will be minus 7 by 4. So I have to take x by 3 to be minimum of these two. So these are all rough. You may do this in rough also, equating denominator to 0. So let x minus 3 to be less than 7 by 8, because this number is smaller, so we will take this to be the bound, half of this to be the bound of this. So then minus 7 by 8 lies between, so this is there, and this implies if I add 3 to both sides, so what I get 24. So 17 by 8 is less than x is less than 31 by 8. So now I want this to be in two forms so that I can multiply them. So I will first so this implies 17 by 4 is less than 2x is less than 31 by 4, and 17 by 2 is less than 4x is less than 31 by 2. So what, now I have to add 3 to both sides. So when I will add 3, it is 29 by 4 less than 2x plus 3 less than 43 by 4, and 17 by, so I have to subtract by minus 5. So this is 7 by 5 less than, so when I will subtract minus 5, so I will get 7 by 2 less than 4x minus 5 less than 21 by 2. Now 8x square plus 2x minus 15 is equal to 2x plus 3 and 4x minus 5, which is greater than equal to 2x plus 3 into 4x minus 5, and this is strictly greater than, I am taking 29 by 4 into 7 by 2. So this number is strictly greater than 7, so I can use 7 above here. No need to solve this complete, so we can take this to be greater than 7. This is greater than 7, so we can put 7 there in our star. Where is the star? So this is the star, so I can use 7 here. So using 8x square plus 2x minus 15 greater than 7 in star, we get what we get. So we had x plus 4, and this was 2x plus 3, 4x minus 5 minus 1 by 9 is less than, using this, and x less than 31 by 8 in star we get. So we have 31 by 8 plus 17 upon 9 into 7, x minus 3. So what we get, 31 plus 17 is 48 by 63, x minus 7. So what delta we should tell? Delta equal to minimum of 63 by 48 epsilon, and we took 7 by 8. So this 7 by 8 is here. Then for this choice of delta 0 less than x minus c less than delta implies x plus 4, 2x plus 3, 4x minus 5 is minus 1 by n is less than epsilon. Hence limit x tends to 3, x plus 4, 2x plus 3, 4x minus 5 is equal to 1 by n, 1 by 9. So this one is question number S. Now we take next question. So what is the next question? Yes. So the next question is, f is given to be R to R. So it is a Dirichlet type of question where at rationals it is defined to be 2x plus 3 and at irrationals it is defined to be x plus 7, and we have to find set of all points C in R such that limit x tends to C, fx exists in R. So for this, let us start. So question number 4, given f from R to R defined as fx equal to 2x plus 3 if x is rational and x plus 7 if x is set of all points C such that limit x tends to C, fx exists in R. So for this what we will do, so let us solve. Now if we are given Dirichlet type of function, then what we to find point C such that limit x tends to C, fx exists, we have to equate the function at rationals with the function at irrationals, and we have to find points of intersection for them. So 2x plus 3 equal to x plus 7 implies x is equal to 4. So we will claim 4 is the only point in R such that limit x tends c equal to 4 is the only point in R such that exists. So for this, what we will do, first we will show that limit. So in case of 4, what is the limit? You have to just put 4 here. So 4, 7, 11. Both the functions give same values. So 11, you have to show let epsilon greater than 0 be any real number. To show there exists delta greater than 0 such that 0 less than x minus 4 less than delta should imply fx minus 11 to be less than epsilon. So this we will show. So consider fx minus 11. So this I can write it as this I can write it as mod 2x plus 3 minus 11 if x belongs to q, and mod x plus 7 minus 11 if x belongs to q complement, and this can be written as, so this is nothing but 2x minus 8, and this is x minus 4 if x belongs to q, if x belongs to q complement, and this can be further reduced to, this is 2 times, so this is 2 times x minus 4 and x minus 4 if x belongs to q, if x belongs to q complement. So this is obviously less than, I can write it as less than equal to 2 times for every x. So this is my star. So what, so let delta equal to epsilon by 2, then by the choice of delta it is clear that 0 less than x minus 4 less than delta implies fx minus 11 is less than epsilon. Hence, limit x tends to 4, fx is equal to 11. So this we have shown. Now to show, next we will show that if c is not equal to 4, then limit x tends to c, fx does not exist. So for this we will use the fact that this we use the fact that c is limit point of both q and q complement. So there exist sequences xn in q such that xn is not equal to c for all n, and yn in q complement such that yn is not equal to c for all n, and xn converges to c and yn converges to c. So this is by density theorem. Oh, this is by the definition of limit point, because c is a limit point of q. So there will be a set sequence of rationals which converges to c, and c is also a limit point of irrationals. So there will be a sequence of irrationals which converges to c. So now what about their corresponding sequences? So f of xn, now f of xn is equal to 2xn plus 3 for all n belonging to n. So this implies f of xn converges to 2c plus 3. Also, f of yn is equal to yn plus 7 for all n belonging to n. So this implies f of yn converges to c plus 7 for now. Since c is not equal to 4, so this implies 2c plus 3 is not equal to c plus 7. Consequently, we have two sequences xn and yn both converging to c, but the corresponding sequences fxn and fyn converges to different limits. Hence, by sequential criteria for limits, limit x tends to c fx does not exist in R. So question number 4 is solved. Now let us move to question number 5. What is the question number 5? So we have to show that the following limits do not exist. The first is limit x tends to c. So we have to show that limit at set of integers does not exist for this greatest integer function. So question number 5, first part, to show limit x tends to c mod x does not exist where c belongs to set of integers. So let us write its proof. So for this, what we will do, we will take two sequences. So let fx equal to mod x for all x belonging to R. So what we will do, we will take two sequences. So let xn equal to c minus 1 by n and yn equal to c plus 1 by n for all n belonging to n. Then f of xn is equal to c minus 1 and f of yn is equal to c for all n belonging to n. So this implies f of xn is a constant sequence c minus 1, so it converges to c minus 1, and f of yn is a constant sequence which converges to c. Xn converges to c and yn is also converging to c. So thus we have found two sequences x and yn both converging to c, but their corresponding sequence fxn converge and fyn converging to different limits. So by thus we have found two sequences xn yn both converging to c, but their corresponding sequences f of xn and f of yn converges to different limits. Hence, by sequential criteria for limits, limit x tends to c fx does not exist. Now let us take its second part. We have to show limit x tends to 0 sin 1 by x does not exist in R. So in this case we have to take we will take two sequences again. So let fx equal to sin 1 by x for all x belonging to R. So what we will do, we will take xn equal to 1 by 2n pi plus pi by 2 for all n belonging to n, and yn equal to 1 by 2n plus 1 pi plus pi by 2 for all n belonging to n. So what we are doing is we are taking this to so that we get 1 f of xn equal to sine of 1 by xn equal to 1, and this will give, because these are odd, 2n plus 1 is an odd term, so when it is in odd, so it falls in third quadrant. So when it falls in third quadrant, so it gives negative value. So clearly xn converges to 0, yn converges to 0. Also f of xn is equal to sgn sine 2n pi plus pi by 2, which is equal to sine of 1, and this is 1. So f of xn is a constant sequence 1, so f of xn converges to 1. Now f of yn equal to sgn of sine of 2n plus 1 pi plus pi by 2. So this will give me sine of minus 1, and this is equal to minus 1. So f of yn is a constant sequence minus 1. So f of yn converges to minus 1. So we have found two sequences again, such that xn and yn converges to 0, but their corresponding sequences converges to different limits. Thus we have got two sequences xn and yn in R such that xn both converging to 0, but their corresponding sequences f of xn and f of yn converging to different limits. Hence, by sequential criteria for limits, limit x tends to 0 does not exist in R. So we are done with question number 5. Let us move to question number 6. So what is the question number 6? Question number 6 is, Give an example of a function f from R to R such that f has limit at x equal to 1 to 3 but does not have limit at all other points. So for this, what we will do, we will take that Dirichlet type function, because we know that if we question number 6, so let define f from R to R such that f of x is equal to x minus 1, x minus 2, x minus 3 if x is rational, and 0 if x is irrational. Then we will show that f has limit at x is equal to 1, 2 and 3, and f does not have limit at c if c is not equal to 1, 2 and 3. So for this, what we will do, so consider, so first we will show that f has limit at, so since we have done many questions similar to this, so I am leaving this to the readers to solve this. I will not do it here. So if you have been given finite number of points, then you can always take those points here and you can define a function like this, and it will have limit at only those points, and it will not have limits at all other points. So it is same, you will take a sequence in rationals that converges to C, and you will take a sequence of irrationals that converges to C, and then you will get that the corresponding sequence does not converge to C, and by that you will be able to prove that these are the only points at which limit exists. So question number now 7. So this is the last question. So what this question says, we have to find condition on x minus 3 that will ensure that 2 root x minus 2 root 3 is less than 1 by 10 raised to the power 3. So this we have already done in one of our videos, so I am not doing it here again. And this question is also has been done in one of my videos. This is in fact question number 16 of Bartle and Sherbert. So this can be seen from there. So again, I am not doing it in this video. Thank you.